Okay, so we're going to start talking about the actual problems. We've already seen the first one. It's just to get started on the first one in the introduction of how to use Caddis. Um, but we're going to look at some of the maybe more interesting problems. All right, so next problem is called Euclid's algorithm. You might have heard of this algorithm from 1820 or other courses, but anyway, it doesn't matter too much. So you're given positive integers a and b. So problem statements is pretty short. You're given positive integers a and b, print the greatest common divisor of a and b. Now, just because it's short doesn't mean that you can just kind of skip over some of the words. First of all, integers, so not real numbers, but also positive. So that means you don't have to worry about negative numbers, but also more importantly, also you don't have to worry about zeros. Okay? So remember that all of these words are there for a reason. So make sure you remember positive means no negative and no zero. Okay, input, first and only line of input contains positive integers a and b, which are at most 10 to the 18. Why do they tell you it's at most 10 to 18? Because that's important. And they're separated by space, so you can read them to two numbers. Print the greatest common divisor of a and b. So if they give you 49 and 91, the answer is 7. If they give you two other numbers, you have to figure out what the GCDs are. Remember that A and B can be in any order. There's no assumption that A is less than B or A is greater than B. And you also have to worry about whether A is equals to B. Now, if you, let's see, where can I find a whiteboard? So, unable to load. Okay, so I'm trying to use a whiteboard here. Why is it not letting me? Okay, I hope that I have managed to get the whiteboard up and going. Okay, so the Euclidean algorithm basically says if you have two numbers A and B, what you want to do when you're going to compute GCD of A and B, it's to basically say what? You want to say if one of them is zero, well, we said that it cannot be zero, but let's just go through the Euclidean algorithm. If one of them is zero, then the GCD is the other one. What if they're both zero? Well, if they're both zero, then the GCD is zero as well. So whenever one of them is zero, the GCD is the other, whether A it's zero or not. Otherwise, you replace A and B with B and A mod B. So when you divide A by B, what's the remainder? And because when you divide by B, the remainder is guaranteed to be less than B, the numbers will be smaller, and you keep going, eventually B has to be zero. So for example, what was it, 49 and 91? I don't remember if that's the input, but let's say that it is. So A and B are 49 and 91. B is not zero, so I have to keep going. I replace it with B and 49 divided by 91, which is 49 remainder. So the first step doesn't seem like it did much. If B is actually bigger than A, the only thing it does is swap them. Now the next step, put 49 back over here, but now you replace 49 by 91 divided by 49 and take the remainder, and it turns out to be 42. Okay, so now you divide again because B is not zero. And this time you put 42 over here, and 49 divided by 42, the remainder is 7. And then you put 7, and then 42 divided by 7. This time it's divided evenly, so it's 0, it's a remainder. So now we have reached the base case, and the answer is 7. So how do we write this? We write something like this: int GCD, int A, and int B. So you write if B it's equal to 0, return A, else return recursively GCD of B and A percent B, like this. Now, this is the standard Euclidean algorithm that you might have learned and written in a recursive way. You can write it in an iterative way if you wish, but it's not really good reason to write it iteratively or recursively one way or another. So whichever way you feel more comfortable, it's good enough. But this is wrong. The reason why this is wrong, it's because they tell you that A and B can be up to 10 to the 18. Now, for most machines, and certainly the ones that we have access to and the one that Caddis uses, ints are 32-bit integers, which means that it can go up to 2 to the 31 minus 1 because it's signed. If you use unsigned int, it can go up to 2 to the 32 minus 1, but it doesn't really matter because this is about 2 billion. And the numbers that you have are way bigger than 2 billion. So just the fact that we're using ints here, it's going to make things fair. So all our variables have to be more than 32-bit integers, and the only other standard things that people can use is 64-bit integers. And as it turns out, 10 to the 18, it's okay. Because if 32-bit integers is up to this much, then 64 bits, it's basically up to the square of this, which is 10 to the 18 and more than 10 to the 18. So we need to use 64-bit integers. And there are two ways you can do this. In the older, and I've certainly done this many times, it's called long, long. So use long, long, replace all of these integers with long, longs. Make sure that all of them are long, long, and then you're fine. Or I guess the newer style, it's int 64 underscore t. So this is an integer, 64-bit integer type. So this is probably what I'll try to do from now on. This is a more standard thing that will work. And it's much clearer than long, long that you are doing 64 bits. And then if you want, instead of using ints, you could use also ints 32t, but int is so common that most people don't bother with that. Okay, so anyway, am I actually still recording? Yes, I think so. Okay, so that's basically what you have to do. So you write this function, you write a main program that read in two variables, A and B, and make sure you don't read them as int. If you try to read them as int, it will be wrong. And then call this function and print the answer. Or, okay, if you actually look at the solution that I have, you will see that my solution looks much simpler. Here's my solution. And I just say, write the function. I told you to write a function GCD, but here I didn't even write any function. Why? because in the new, well, in the C++ 17 and beyond, GCD is part of the standard library, and it's a template function, so it will work for any integer type. And then I guess you don't really care how it's actually done because, we just use it. Now you might also say, okay, I told you that for the first set of problems, timing of how long your program takes probably wouldn't matter. You have 1 second, and these numbers are very big, right? 10 to the 18. And you might think 10 to the 18 is really big number, but 10 to 18 is actually not very big number because it's only 18 digits long. So if we think about the numbers in terms of the digits, it's actually really small. And Euclidean algorithm, actually the complexity of Euclidean algorithm is sort of proportional to the number of digits. Because every step, when you divide A by B, the number of digits will go down to be smaller, more or less smaller than the number of digits in B. Not quite exactly, but the few steps, it will happen. Okay. So Euclidean algorithm is actually really fast. Okay, so that's that one. And you can certainly do it without knowing the fact that GCD is already in the library. But if you know, right, then of course the problem becomes trivial. So the main thing is, part of it is, to do the problems, but also as you go through these, try to learn what's actually available in the library. Okay, next problem, and days of Christmas. So you have this songs of N days of Christmas. So every day it's one of something, the next two of something, three of something, four of something. So basically on the Dth day, you have D of something plus D minus one of something plus D minus two of something. In other words, it's 1 plus 2 plus 3 all the way up to D. So you want to know on a certain day, so in this case, they want to generalize on an nth day, how many gifts do you receive? So it's 1 plus 2 plus 3 all the way to n. And also, what is the total number of gifts you have received by the end of the 12th day? So not only do you want to know what you got from the 12th day, you want to know what you got from the 11th day, 10th day, and so on all the way to the beginning. Given n, what are the answers to generalized versions of the two questions above? The input consists of a single integer n, which is the number of days of Christmas. And in this case, the n is between 1 and 366. So how much time do we have? 1 second. Now, we don't have to worry too much about this 1 second because the input is at most 366. So whatever reasonable things you do, it's probably good enough. So the first question is, how do you get the answer to the first question? How many gifts do you receive on 12 days? So that's 1 plus 2 plus 3 up to n. And you can either just do that, write a for loop that add it all up, or you can remember that there's a formula for that, and the formula was n times n plus 1 over 2. Okay, you can look that up, you can work it out, or maybe you just remember that. Either way, that's a very important formula, useful formula that you should definitely know it by heart. And then what is the total number of gifts you have received by the end of the 12th day? Well, if you know how many gifts you receive on each day, well, then you just, write a loop and add it all up. Again, you can come up with a formula, but this time the formula would be a little bit more tricky because you'll be adding formulas that involves inside would be n times n plus 1 over 2, and it's not as simple. If you're a math major, maybe you can figure out how that works. If you really want to know and you don't know that already, you can either look it up or you can come ask me, and I can show you how to actually get this closed form formula. but because the numbers are so small, we might as well just do a loop to add it all. So I'll just quickly show you my solution. Okay, you might ask, what is this wrong answer? Because I didn't read the problem. And I did something completely different. So I didn't even try to compile and test it. That's why I was wrong on the very first case, the sample input. Okay, so you read and the two things that you want is the sum of the first n numbers, and then I just call it f. Again, you might want to come up with more descriptive names. If it was a problem as simple as this, I don't really usually bother. So what does the sum do? It computes the formula 1 plus 2 plus 3 up to n, which is n times n plus 1 over 2. Maybe you think this is simple, but when I'm writing this, you always have to worry about two things. First, is integer enough to hold the answer, right? We just in the previous example, previous problem, we have cases where the numbers are so big that int is not big enough. But in this case, they tell you that it's at most 366. This is at most 366 squared, which divide by 2 and a little bit, but 366 squared is actually only, well, so let's just say it's less than a million, and it's good enough. Integer is good enough. And similarly, you can do an analysis here to make sure that the integer is big enough for the other answer. So for the other answer, the other thing is I have n times n plus 1 over 2, but whenever you write over 2 in C++, you always have to worry about, am I dividing by integer or am I dividing by non-integers? Do I want to divide as doubles? Do I want to divide by integers? Am I going to get messed up if I'm trying to divide by 2, but what I'm dividing by, it's odd. Okay, all of that, it's important to think about. But in this case, it's okay because I do things from left to right. And n plus 1, one of them has to be odd and one of them has to be even. So when you multiply them together, the answer is always going to be even. You divide by 2, it's okay. You're not going to lose a half somehow. Okay, but even something simple as this, you want to think about this, at least in your head, to make sure that you're not making a silly mistake. All right, the second part is to sum up the answer for the first n days. So I have an answer that's 0, start at 0, and I just loop through. And this time I have to remember that my loop is not the usual 0 to n, I equal to 0, I less than n, but I need to make sure that I call sum of 1, sum of 2, all the way sum of n, not sum of 0 all the way up to sum of n minus 1. Okay, so I have to be a bit careful here. But other than that, that's pretty much this problem. Okay, let's look at the next one. Now, the next one basically is a selection sort. Right, so you have up to 1,000 cases. Each case is processed separately. It doesn't really matter. We just look at one case at a time. It has data set number k, which is supposed to just print it out, followed by 20 non-negative unique numbers. Okay, so this sentence is very loaded. There are 20 numbers. Each one is non-negative. Non-negative means that 0 is allowed. They are unique. Okay. So there are no two people with duplicate. And because this problem is about sorting, when you have non-unique entries, then it's maybe a little bit unclear who should be standing in front of the other when two people are the same. And 20 integers represent heights, millimeters of each student in the class. All right. What you're supposed to do is figure out how many people you could basically, if you read this problem, you're basically doing insertion sort. You start with the first student and you just keep on sorting them, and every time you ask, where does this person go? Where does the next person go? And based on that, you figure out how many you have to shift. Now, because there are only 20 people, you could actually just implement insertion sort using your favorite reference or you do it yourself. and then count every time you insert somebody, how many steps you move. Okay, so go and look up insertion sorts and okay, try different things. Yeah, again, you see, I didn't even bother reading the problem and I got it wrong in the sample input the very first time. But anyway, I have two versions here. Okay, so let me just start with the main program. So the main program, I start with the number of cases, and then I just write a for loop that call a function called solve case. I generally like to do this instead of writing one big main program, and that's because you know there is nothing that you need to save from one case to the next. So by making a function and making all the variables local, you don't have to worry about accidentally carrying something from one case to the next. Okay, so I have the problem ID. I have the number of items, which in this case is fixed at 20, and I can declare an array of size 20. I read in the ID, and then I write a for loop that reads in all the array elements. I know a lot of people I see didn't know, maybe they don't know that you can read directly the a bracket I. So I've seen all the time people reading in some temporary integer variable and then assign that integer variable into a bracket I. You don't have to do that. You can just read it directly. Now, let's look at this version, which is a standard insertion sort. So you can probably look up or come up with your own version of insertion sorts. And basically every time I do a swap, I increment the counter so I remember how many swaps I've done, and that's the answer. Okay, I'm not going to go through what insertion sort is and how you code it. If you have knowledge up to 2620, you should know this by now. If not, you can look that up. But I want to show you an alternate solution. Oh, the other thing is swap. You don't have to write swap yourself. Swap is part of the standard template library. Okay, I want to show you an alternate way of doing things. I'm not saying it's better, but I want to show you an alternate way. So what is an insertion sort? Insertion sort keep the first bunch of things sorted, and then I have to swap the next thing into the correct position. Now, maybe I don't want to think about it, how insertion works. So I'm just going to tell the C++ library sort the first part. Is it any better? No. In fact, it's slower if you trigger STL sort every time. But it's faster for me to type. It's faster for me to think about. And so for a problem in which the size of a problem is small, I don't really need to optimize for execution time. I can be wasteful in my CPU cycles of the program. What I want to optimize is my thinking time. Okay? So why do I say thinking time? Why is it less thinking time? Because this is single for loop. This is a nested for loop. Nested for loops are generally harder to think about and harder to get right. And I replace the nested for loop, the inner loop, with functions that are provided by STL. Even if it's not as efficient, it's more efficient for me to think about them. Okay, so I say sort the first I minus one items. And then to figure out where to swap it to, I don't even bother doing the actual swap. If the first part is sorted, I can ask binary search. So lower bound in binary in STL gives me the first position in a sorted array. So the sorted array is this part. The item that I'm looking for is this. It gives me the first position in the array that is not bigger than the item that I'm looking for. If you think about this carefully, it means it's the place where I should insert my item. Okay, there's a lower bound, there's an upper bound. It basically is binary search. The lower bound means basically this is a place that I should insert, and upper bound means if I have a bunch of items that like AI, if I'm looking for an item and that item appears multiple times, it will be it will be the first item that is bigger than the item that I'm looking for. So if you think about that, that's one past the n of a bunch of items that you're looking for. But anyway, lower bound, it's going to tell me, it's going to return a pointer and an iterator to the place where I should insert. So minus the beginning of the array will be the actual position. Okay, remember that these are not positions, they're pointers. So if I want to get the actual position, I need to do some pointer or iterator arithmetic. And then if I'm inserting position 2, let's say, how many positions did I have to shift? Well, if I have 5 things that are sorted, so I would be 5, and I'm inserting position 2, then the number of things I have to shift is the difference. 5 minus 2. I have to shift 3 things, right? So that's how I count them, and then I just add it to my power. So is this better? In terms of runtime, absolutely not. In fact, it's way worse. If n is big, there's no way I'm going to use this approach. Well, but then if n is big, you probably shouldn't be using insertion sort anyway. Okay, but it saves me in terms of thinking time. All right, now the next 2 problems, they are a little bit more thinking problem, and I'm not going to really show you too much of the code, but I want to maybe talk about how to think about these problems, how to do them. Okay, so you have a bunch of socks, okay, n of them, and groups of socks. And then each of these group can be either, so there's a type of socks, a name, and it could be left socks, right socks, or it could be either. And then each of those could have a certain number. Okay, and your goal is to figure out how many socks you need to pick up randomly from the drawer to ensure that there's at least one matching pair, or output if it's not possible. Okay, so let's think about this a little bit. So for example, here, Annie, they have all the same type of socks. So what can match? 2 Annie can match. A left and an Annie can match, but 2 lefts cannot match. So what we actually want to do is to figure out what is the maximum number of socks you can pick and not have a match, and then add 1 more. Okay, if possible. So let's look at some simple example that they show you so to just try to figure out. Sample inputs are not exhaustive, so there might be cases that are not covered, but at least we should make sure that we work on the sample input. Things will work on the sample input and then maybe generalize from there. Okay, so there are 2 types of socks here, fuzzy and wool. Fuzzy, there are 10 of them. Any of them can match any of them. So if you pick 2 fuzzy socks, then they will match. If I want to pick the maximum number of fuzzy socks to ensure that nothing matches, the maximum I can pick is 1. Okay, so if I pick up an any sock, I cannot pick up 2 of those. Okay, so that's the first observation. Second observation here, I have wool that have 6 left and 4 right. How many can I pick up, and what is the maximum number of wool socks I can pick up and still not have a matching pair? Well, I can pick up 4 right, or I can pick up 6 left. So the maximum I can pick up is 6 and still not have a matching pair. But as soon as I pick 7 wool socks, I'm guaranteed to have a matching pair. Okay? So in the case of here, when I have some socks that have both left and right, I want to pick the maximum of the left or the right. And that will ensure that I still don't have a matching pair. Okay, here I have sports, black and white. Black has only left socks, so there's no way you can match them. White has only white right socks, so you cannot match them. Sports, it's any, but there's only one of them, so there's no way you can match them. So now you ask, okay, when is it impossible? If for every sock type, either you only have left or you only have right, or you have any, but I only have one. Okay. What if you have only one any, but you also have some left socks of the same type? Well, then you can match them. Okay, but there's three conditions that you need to check for. Either you only have left and no right and no any. Either you only have right and no left or no any. Or you have any, exactly one any, and no left and no right. So you can kind of work out what kind of expression you need. You check for any, it's one and the other two are zero. Or you check for left is non-zero, but the other two are zero. Or you check for right is zero, non-zero, and the other is zero. Now, this is a little bit of a, there's another way here. Any and left, right? Any, you can only pick one of them. But left, you can pick three of them and still not have a matching pair. So basically, there are two problems. The first problem is we have to manage to figure out for each type of stocks how many left, right, and any there are. So you have to have some way of grouping things that are the same name together. And then the other thing is once you have the correct numbers for each type, you have to go through the types and then figure out what you can do. Also, a given fit of a given type of sock appears at most once in the input, so you were not going to have two entries, fuzzy any10 and then fuzzy any5. Okay, so you don't have to worry about that. So how do we keep track of this information? Well, you need to have things classified by the type. So the best way to do it is actually a map. Use a map where the key is the name of the socks. And you keep track of three numbers. How many left you have, how many right you have, and how many any you have. So I'll just show you, start from my code. I'm going to have a structure that keeps track of the three numbers, left, right, and any. Okay, that's the first thing. And then I have a map that keeps track of the counts indexed by the name of the sock. Notice I'm using global variables here. I know that these are things that you're not supposed to do in all your other courses, but for this type of problem, when you're only dealing with one single case, it's okay. All right. So I read in n, which is a number of entries, and then for each type, for each entry, I read in I, j, and k. Now, you might say, well, I, j, and k is, not so great variable names, but these are exactly the variable names that I use in the problem statement, and I generally like to stick with them because then I don't get confused reading the statement followed by reading the my code. But of course, when they use I, j, and k, you better make sure that if you write loops, you don't end up using I, j, and k, right? Anyway, so that's why I have a loop that using this is t, let's say. So I read in I, j, and k. And then if I say, is it any, is it left, is it right? And then if it's any, then I would say sock bracket I dot any, it's k. So this will go to the entry for sock. If there was no entry for that sock before, it will initialize it to 000, the default constructor. Otherwise, whatever entry was there already, it would just keep, and I just initialize the corresponding field with the right number. So now Now what? I want to know what is the maximum number of socks I can pick and still not have anything matching. So my answer, it's going to keep track of that for now. I'm going to loop through my map. And this is a way to loop through my map. Remember that each entry in a map is a pair of key and value. So the key is a type. So this is in C++17. You can use this auto square bracket type and C, and we'll go through the loop, go through the entire container, and each entry will assign the key to the type, the value to C, and then it will loop through the entire map. So here, that's what it is. I look at the maximum of left and right. If I don't have, I can pick all left, I can pick all right. If I have any socks, any type socks, well, I can pick at most one of them. So I do a minimum one C.any. In case C.any is zero, that will be zero. But if it's anything more than one, it will make sure that I can make most one. And then I take the max of the three things. Either I can pick all left, I can pick all right, I can pick one of the any. And of course, you only pick one of the any if left and right are zero. And that's the maximum number of socks I can pick from that type and still not have a match. Okay, we'll ignore that possible for now. And if it's possible, then I just take that answer plus one, and that's my answer. Now, I also need to know if it was at all possible to find a matching pair to begin with. How do I know? At the beginning, nothing's possible. For each type of sock I check, is it possible to have actually that type of matching, right? So how can it be? Maybe it's because you have at least two of the any type. Or maybe you have at least one left sock, and at least one of the other two socks, or vice versa. Now I'm doing, this three lines of code actually have a lot of things going on. First of all, possible is a Boolean value. It's initialized to false. I'm saying whatever possible, I want to make it true if any one of these three conditions are true. But if it was true already, I don't want to turn it false. So here, remember, it's like plus equals. If I have an integer variable, I say plus equals, A plus equals B, that means A equals A plus B. So here, possible, it's equals to possible or this condition. So it's whatever it was before, or if this is true. So we'll turn possible to true if this is true. And if it's not true, it will just keep whatever it used to be. The second thing is that notice I'm not using any if statements at all, because all of these are Boolean values. They have their own true or false. I don't need to write if this is true, then do something. This is itself a Boolean value. And third thing here is that I use things like c.left and c.right. They are actually an integer count, how many left and right socks I have. But I'm using them as Boolean because I want non-zero to be true and zero to be false. So c.left just means I have any. Now I have non-zero number of left socks. And here I'm saying I have a non-zero number of right socks or a non-zero number of any socks. Okay, so this is like three lines of code, but there's actually a lot of stuff going on in there. But anyway, that's all I want to show. I don't want to go too deep into the detail. And the last problem I want to talk about, I'm not even going to show you the code. I just wanted, this is a slightly more advanced problem. I assume you read it, so I'm just going to go to the whiteboard. Am I showing the whiteboard? Where's the whiteboard? Okay. Clear the whole thing. How do I clear the whole thing? Clear page. All right. So you have a refrigerator and you have a bunch of slots. I'm just going to say this is a front and this is a back. Let's just say you have 4 slots, and there's a certain number of each slot you can put in a certain number bottle of whatever it is that they want to keep. So there's D of them. And change colors. Color. Okay. Each of these already have some drinks in them. Some have more, some have less. These are the cold ones. You need to stock new drinks and you put them in the front. So for example, you want to stock things here, you're going to put them here. You need to stock a certain number of drinks. I think it's N drinks. And anything that you stock will not be cold, right? So that's why it's red. You want to get the blue ones. Now, M people are going to come and randomly grab a drink from the front. And you want to minimize the probability that any of them will grab a warm drink. Now, if you were to fill these 3 things, instead of filling them here, maybe you spread them out. Now, the first person would have only a 1/4 chance of getting a cold drink. Whereas if you didn't have that, like this, then the first person will have only, we have a 3/4 chance of getting the right drink. So basically, if you think about it for a while, the intuition is that you want to minimize the number of slots you use. Okay? You want to try to fill as many into 1 slot and only use 2 slots if necessary and only use 3 slots if necessary. So if you think about it again, if you think about this requirement again, what you want to do is you want to take the slot that has the most number of free spots, or in other words, the fewest number of drinks that are already there, and use all the spots as much as you can to fill the N drinks. If you fill up all the N drinks, if you use up all the N drinks you need to fill, you're done. What if you still need to fill more? Well, then you use the next one. Next one is over here. And so on. That is the best possible way, because that keeps the most number of unfilled container slots that are all cold. So that's the first step, is to realize that you want to sort things by the number of items already there and fill them from the smallest one to the biggest one, because the smallest one means you can fill the most. The next question is it impossible? Is it possible? Impossible means you cannot satisfy M people. So how do you know? So in this case, how many people can you satisfy? Well, if somebody goes and accidentally pick these 2, that's bad. So the only way you can satisfy everybody is if everybody picks these 2. Basically anything that is unfilled, right? They can only pick from slots that are unfilled. So how many? How many actual cold bottles can you get? Well, you add up these, in this case 10, and if the number of cold drinks that are accessible is 10, and you have 10 or fewer people, you're good. If you have more than 10 people, then there's no way you can satisfy this request. So you say impossible. Okay, so there's a little bit of thinking about, how to optimize, because they ask you to optimize the probability that everybody gets a cold drink. So you have to think about that a bit. Then you have to think about how to deal with the impossible. And if you got all of that, then you have to think about well, how you actually uh, implement this. So I'm not actually going to show you code. You can look it up on my GitHub repository if you want. This is a problem that's meant for more advanced people, but still, even if you're just starting out, you should still look at my solution, see if you understand it, and think about how to maybe try to do it yourself even after reading my code. Okay, so I'm going to stop here for this week. As usual, if you have any questions, feel free to contact me through Discord or through other ways. And then we'll see you again next week with a different problem set.